Good day everyone, and welcome to where we are putting together solutions in the subject of additional mathematics. This video looks at section 3, Introductory Calculus, and it looks at the first 5 years of the past paper questions in paper 2 from May 2012 until 2016. Don't forget to like the video and add any comments down below so we can help create other videos to assist you in your understanding of the subject area. If you look at the description down below, it highlights the order we suggest that you go through the entire past paper solutions in order for you to get a better grasp of the subject area. Let's look at the 4 major sections of the CSEC Additional Mathematics syllabus. And in this video, we'll be looking at section 3, Introductory Calculus. This topic is tested for 10 out of the 45 questions in paper 1 and 30 marks out of the 100 in paper 2. This has 2 major sections, the first being differentiation, which is subdivided into the gradient of a curve and the derivative as a limit. The first and second derivatives, which are represented as f prime x, dy dx, and f double prime x. Another subdivision is the derivative of x to the n sine ax, cos ax, c fx, fx plus or minus g of x. We also need to know the chain, product, and quotient rules, the equation of tangents and normals, and the nature of stationary points, whether there's a sign change or using the second derivative. And you can see some of the formulas given in the formula sheet include the differential of ax plus b to the n, differential of sine ax, and differential of cos ax. The second part of calculus will be the subtopic of integration. This is subdivided into indefinite integrals, which are the integrals of f of x, integral of c f of x, integral of fx plus or minus g of x. Integrate polynomials, which include integral of ax plus b to the n with respect to x, where n is not equal to 1. Integrate with trig ratios, which includes the integral of a sine px plus or minus b cos qx. Finding the definite integrals, integrating f of x from a to b, which means f of b minus f of a. Finding the equation of a curve given the gradient, function, and a point. And of course, finding the area of a region in the first quadrant, and volumes of revolution. Differentiation has been tested as number 5 in each of the first 5 years, and integration as number 6 in all 5 years. May 2012, number 5a, differentiate the following expression with respect to x, simplifying your answer. And the expression is an algebraic fraction where its numerator is 3x plus 4 and the denominator is x minus 2. So we want to find the differential of this quotient. And notice we're writing the numerator in red and the denominator in green to assist students in understanding it. So let's recall the quotient rule with respect to differentiation. So d dx of u over v will be the denominator v du dx minus u dv dx all over v squared. And we're trying to maintain that color code so students can follow. So if we differentiate 3x plus 4 over x minus 2, then the denominator comes outside as v, which is x minus 2, by the differential of u, which is 3x plus 4, minus u, which is 3x plus 4 by d dx of x minus 2, all over x minus 2 squared. Don't forget to put the denominator. So we can differentiate. So it'll give us x minus 2 by what's the differential of 3x plus 4? That is 3. We can think of it a couple of ways. We can differentiate each term. So if we differentiate 3x, it's going to give us 3. And if we differentiate a constant 4, it's going to give us 0. Or we can consider that 3x plus 4 is a straight line. And the gradient of a straight line would be the coefficient of x. So that will give us 3. Minus 3x plus 4 by differentiating x minus 2. And that will give us 1. So we can now expand the numerator. So 3 times x minus 2 will be 3x minus 6. Minus 1 times 3x plus 4 will give us minus 3x minus 4. All over x minus 2 squared. And now we can simplify the numerator. It will give us 3x minus 3x is 0. So minus 6 minus 4 is minus 10 all over x minus 2 squared. Part B, the point P, 210, lies on the curve y is equal to 3x squared plus 5x minus 12. So we're looking at a quadratic curve, so we can bring up that sketch. And we can now highlight that point P, which lies on the curve at the x value 2 and y value 10. Find equations for part 1, the tangent to the curve at P. So let's bring up a tangent at P. We have that showing a green line. And we can see from this sketch here that the slope is going up to the right, which means at this point the gradient is positive. Now something to remember, if we rewrite the equation y is equal to 3x squared plus 5x minus 12, and we look at the sketch, at every point on the curve, the gradient will be changing. On the left-hand side, it will be negative. By the time it hits the minimum point, it's 0. And when it's coming up on the right-hand side, it's positive. So how do we find the gradient? That's done by finding the differential. When we differentiate 3x squared, it will give us 3 2 are 6, x to the power 2 minus 1, which is 1, so 6x, plus 5x minus 12, the differential of that is 5. So what this tells us is that for every value of x, it will give us a different gradient. And what's the value? We need to substitute it into dy dx, into 6x plus 5. And at the point P, x is equal to 2. So if we substitute, it will give us dy dx is equal to 6 times 2 plus 5, which is 6 2 are 12 and 5 is 17. So the gradient is 17. And it follows because the gradient is positive. And that green line is sloping up to the right, shows that the gradient is positive. So if you want to find the equation of the line, we know that the gradient of that tangent, m with a subscript t to represent that, will be equal to change in y over change in x. So if we substitute, it's going to give us 17 is equal to y minus, what's the y value at P? 10 over x minus, what's the x value at P? 2. Because if we're looking at the tangent, we need to have a point on that line. And one of the points on that line is P, which is 210. Now that we have substituted, let's transpose to make y the subject of the formula. So let's carry across the denominator x minus 2. So it'll give us 17 times x minus 2 is equal to y minus 10. So let us now expand the left-hand side using the distributive law. So 17 times x is 17x, minus 17 times 2 is 34. And if we move the minus 10 across to the right-hand side, it means plus 10. As such, we can simplify. So y is equal to 17x minus 24. That is the equation of the tangent to the curve at P. Part 2. Find the equation for the normal to the curve at P. As such, we know that the tangent and the normal are perpendicular to each other. So if you multiply the gradients, the gradient of the tangent times mn, the gradient of the normal, is equal to minus 1. And if we substitute 17, which we worked out in part 1, times the gradient of the normal is equal to minus 1. As such, the gradient of the normal, m to the subscript n, will be equal to minus 1 over 17. And if we want to find the equation, then we follow the same format as we did in part 1. So m to the n is equal to change in y over change in x. And if we substitute, minus 1 over 17 is equal to y minus, and the normal is still passing through that point P, which is 210. So it will give us y minus 10 over x minus 2. And we transpose until we find y. So let's carry the denominator across. It will give us minus 1 over 17 times x minus 2 is equal to y minus 10. Let's expand the left-hand side and carry the minus 10 across. So it will give us minus 1 over 17 times x, which is minus 117x, plus 2 over 17, and we carry the minus 10 across, plus 10 is equal to y. As such, y is equal to minus 117x plus 10 on 217s. And we have that in that purple line there to indicate such. May 2012, number 5C. The length of a side of a square is increasing at a rate of 4 centimeters per second. And we can see that in a little sketch. Find the rate of increase of the area when the length of the side is 5 centimeters. So this is a rate of change question, and we know dA dt, that the rate of change of area, is equal to dA dL times dL dt. So if we cancel off the dLs on the right hand side, we'll be left with dA over dt. Now what is the area of a square? Area is equal to L times L, which is L squared. So if we differentiate that formula with respect to L, dA dL will be equal to 2L. We want to find out when L is equal to 5 centimeters. So dL dt, which is the rate at which the length of the side is increasing, is equal to 4. So if we substitute in the formula, dA dt is equal to dL dt times dA over dL, that will give us 4 times 2 times 5, because L is 5. And that works out to be 40 centimeters squared per second. And that is the rate at which the area is increasing when the length is 5. May 2012, number 6a. Evaluate 16 minus 7x to the power 3 from the limits 1 to 2 with respect to x. So this is a definite integral. And let's recall that if we integrate ax plus b to the n, will give us ax plus b to the n plus 1 over a by n plus 1. So if we simply substitute for that, then it will give us 16 minus 7x to the power 3 plus 1 all over, what's a? Minus 7 by 3 plus 1, between the limits of 1 and 2. So that gives us 16 minus 7x to the power 4 all over minus 28 from 1 to 2. And if we want to evaluate that, we can extract the minus 1 over 28 on the outside and substitute accordingly. So that will give us minus 1 over 28 by 15 minus 7 times 2 in brackets to the power 4 minus 16 times 7 times 1 in brackets to the power 4. And we can work that out. So it will still be minus 1 over 28 on the outside, and 16 minus 7 2s are 14. 16 minus 14 is 2 to the power 4 minus 16 minus 7 to the power 1, which is 16 minus 7, which is 9, 9 to the power 4. And we can expand, so that will give us minus 2 to the power 4 is 16, minus 9 to the power 4 is 6,561, all over 28. And that works out to be 6,545 over 28, which can be reduced by dividing by 7, so that will give us 935 over 4. And that will be the value of the definite integral. Part B. The point Q, 4, 8, lies on a curve for which dy dx is equal to 3x minus 5. So let's bring up a sketch of 3x minus 5, which will be sloping up to the right. We have that in red. And the point Q, where it's passing through, which is 4, 8. Determine the equation of the curve. So since we know the gradient is 3x minus 5, let's work backwards. Can we find y, the equation of the curve? We can do that by integrating. If we integrate the differential equation with respect to x on both sides, then the integral of dy dx with respect to x is y, which is equal to the integral of 3x minus 5 with respect to x. So that will be 3x squared over 2 minus 5x plus c, a constant. And at the point Q, what do we know? We know the x value is 4 and the y value is 8. So we can substitute. So that will give us 8 is equal to 3 over 2 by 4 squared minus 5 by 4 plus c. So 8 is equal to 4 4s are 16, 2 into 16 is 8, 8 3s are 24, minus 5 4s are 20 plus c. 24 minus 20 is 4. If you carry it across, 8 minus 4 is 4, is equal to the constant of integration c. So y is equal to 3 on 2x squared minus 5x plus 4. May 2012, number 6c. Calculate the area between the curve y is equal to 2 cos x plus 3 sin x. So let's bring up that curve in red. And the x-axis from x is equal to 0 to pi on 3. So let's use our blue line to show x is equal to 0, which is the y-axis. And let's bring up a green line to show x is equal to pi on 3. And of course, the x-axis, we could have that as a purple line. So what we actually have is a region in which there are 4 sides that have been identified. So what we want to find is that area. So you could bring it up in the green so you could see it. So the area of this shape is the definite integral of y with respect to x from a to b, the limits on the x-axis. So it's the area of 2 cos x plus 3 sin x from 0 to pi on 3, those are x values, with respect to x. And if we integrate, it will give us 2 sin x minus 3 cos x from 0 to pi on 3. We can now substitute the values. So it will give us 2 sin pi on 3 minus 3 cos pi on 3 minus 2 sin 0 minus 3 cos 0. And we know sin pi on 3. Pi on 3 is 60. So sin pi on 3 would be root 3 on 2. So that will give us 2 root 3 on 2 minus 3 by cos 60, which is a half, minus 2 times what's sin 0? 0, minus 3 times cos 0, which is 1. So we can simplify. So it will give us root 3 minus 3 ones are 3 over 2 minus 0 plus 3. And if we simplify, it will give us root 3 plus 3 minus 3 on 2 is plus 3 on 2 square units. Last part of the question. Calculate the volume of the solid formed when the area enclosed by the curve y is equal to x squared plus 2. And let's bring up that curve in red. And the x-axis, which we have in purple, from x is equal to 0, which we have in blue, that blue line, to x is equal to 3, we have in that green line, is rotated through 360 degrees about the x-axis. So let's show the revolution of this green area about the y-axis. Leave your solution in terms of pi. So how do we find that volume? So volume is equal to pi by the integral of x squared plus 2 all squared with respect to x between the limits of 0 and 3, because those are your limits along the x-axis. One way to work it out would be just to expand the quadratic, and that will give us volume is equal to pi by the integral of x to the 4th plus 4x squared plus 4 with respect to x between the limits of 0 and 3. And if we integrate each of the terms, it will give us pi by the integral of x to the 4th is x to the 5th, 4 plus 1 is 5, all over 5, plus 4 times x to the power 2 plus 1 is 3, all over 3, plus 4 times x, between the limits of 0 and 3. And of course we can substitute now. So volume is equal to 3 to the power 5 over 5, plus 4 times 3 to the power 3 over 3, plus 4 times 3, minus 0 to the power 5 over 5 plus 4 times 0 to the power 3 over 3 plus 4 times 0. And you can see the whole right hand side will be equal to 0. So that will be left with v is equal to pi times 3 to the power 5 is 243 over 5 plus 4 times 3 cubed, which is 27, all over 3. 3 into 27 is 9. 9 4s are 36 plus 4 3s are 12. 36 plus 12 is 48. And that will give us volume is equal to 483 pi over 5 cubic units. May 2013, number 5a. Given that y is equal to x cubed minus 3x squared plus 2, find the coordinates of the stationary points of y. We know at the stationary points that the gradient is equal to 0. And how do we find the gradient? By differentiating. So dy dx will be d dx of x cubed minus 3x squared plus 2. The differential of x cubed will be bringing the 3 in front, will give us 3x to the power 3 minus 1, which is 2. So 3x squared minus 3 2s are 6x. And if we differentiate 2, it will give us 0. So dy dx is equal to 3x squared minus 6x. And at the stationary points, it means that dy dx is equal to 0. So if we substitute 0 is equal to, and we can factorize the right hand side, 3x by x minus 2. Either 3x is equal to 0, which means x is equal to 0, and we can substitute to find the y value there. So y is equal to x cubed minus 3x squared plus 2. If we substitute x is 0 into there, y is equal to 0 cubed minus 3 by 0 squared plus 2. So y is equal to 2. Therefore, one stationary point will be at the point x is equal to 0, which is the y-axis, and y is equal to 2. So we have indicate that with a red line. The other brackets, x minus 2 is equal to 0. So x is equal to 2. So we can bring that up. That will be a stationary point as well, meaning the gradient will be 0 there as well. So y is equal to x cubed minus 3x squared plus 2, and we can substitute for x equal to 2 into there. So it will be 2 cubed minus 3 by 2 squared plus 2. 2 cubed is 8, minus 3 by 2 2s are 4. So 8 minus 12 is minus 4 plus 2 is minus 2. So the second stationary point will lie at the value 2 minus 2. So we have the first one in red and the second one in purple, and we can see our sketch in green there. Part 2. Find the second derivative of y, and hence determine the nature of each of the stationary points. So of course, if we want to find the second derivative, that's d2y dx squared is equal to d dx of dy dx, meaning we have to differentiate whatever dy dx is. And in part 1, we worked out dy dx in the second line, so we can substitute that d dx of 3x squared minus 6x, and if we differentiate 3x squared, 3 2s are 6, will give us 6x minus 6. So that's the differential. So when x is equal to 0, which is the red line, we want to find out whether it's a maximum or minimum, so we can substitute into d2y dx squared, so it will be 6 by 0 minus 6. 6 zeros are 0, 0 minus 6 means we're getting a negative, something less than 0. As such, that is a maximum point of the graph. At the purple point where x is equal to 2, so if we differentiate d2y dx squared into that, it will give us 6 by 2 minus 6. 6 2s are 12, 12 minus 6 is something positive, which is greater than 0. And as long as we have an answer greater than 0 or positive, it means a minimum point. So we can bring up the sketch. Part B. Differentiate y is equal to 5x plus 3 cubed sine x with respect to x, simplifying your result as far as possible. So that looks like a product rule that we can use. So d dx of 5x plus 3 cubed sine x. And if we recall the product rule d dx of uv, notice we have the first term in red, that's u, and the second term in green, that's v. So the differential of uv will be u dv dx plus v du dx. So we can substitute accordingly. We know u and we know v. So that will give us 5x plus 3 cubed by d dx of sine x plus sine x by d dx of 5x plus 3 cubed. And we can solve the differential, so it will give us 5x plus 3 cubed by the differential of sine x is cos x plus sine x by the differential of 5x plus 3 cubed. We can bring the 3 in front, bring the 5 in front by 5x plus 3 squared. So that gives us 5x plus 3 cubed cos x plus sine x by 15 5x plus 3 squared. May 13, number 6a, evaluate the integral of 5x squared plus 4. So this is an indefinite integral, which means that we're going to have a constant of integration. So if we integrate 5x squared plus 4 dx, that means you can take out the 5 outside, so it'll be 5 times the integral of x squared plus the integral of 4, both with respect to x. So if we integrate x squared, then it'll give us 5 by x to the power 2 plus 1, which is 3, divided by 3, plus 4x plus c. Don't forget the c, the constant of integration. Part B, evaluate 3 sin x minus 5 cos x, the integral of that, between the limits of 0 and pi on 2. So this is a definite integral. As in the case of definite integrals, the constant of integration when we substitute will cancel off. So some people put in the plus c, some people leave it out. It's fine, it will disappear at the end. If you integrate 3 sin x, it will give us minus 3 cos x, and minus the integral of 5 cos x will give us minus 5 sin x, between the limits of 0 and pi on 2. Now another way to be looking at this, that we're finding the integral of 3 sin x means that we bring up 3 sin x, we're finding the area under the graph between the limits of 0 and pi on 2. Pi on 2 would be 1.07, 3.14 divided by 2. So that we can see that's positive. And the integral of minus 5 cos x, which we have in purple. And if we're still between the same limits of 0 and pi on 2, we can see that that is negative. So let's see when we evaluate if it's similar. So if we substitute now, minus 3 cos pi on 2, minus 5 sin pi on 2, minus minus 3 cos 0, minus 5 sin 0. We're substituting for the two limits. So minus 3 cos 90, remember cos 90 is 0. Minus 5 by sin 90 is 1, so minus 5 by 1. Minus 3 cos 0 is 1, so minus 3 by 1. Minus 5 sin 0, which is 0. So that works out to be minus 5 minus 3, which works out to be minus 5 plus 3, which is minus 2 square units. So we can see that the area under the red line, which is the sin x part, is positive, and the area above the purple line is negative, and the negative area is more than the positive area. So if we add them up, we're going to get something which is negative. A curve passes through the points P, 0, 8, which means it's cutting the y-axis at 8, and Q, 4, 0, so it's cutting the x-axis at 4, and is such that the gradient is 2 minus 2x. Find the area of the finite curve bounded by the curve in the first quadrant. So if we know the gradient function, we can find y by integrating both sides with respect to x. So if we integrate dy dx, which is 2 minus 2x, that will give us y equal to 2x minus x squared plus c. And if we substitute at the point P, we know the x value and y value, so we can find out c, the constant of integration. So 8 is equal to 2 by 0 minus 0 squared, because at the point P, y is 8 and x is 0. So that gives us 8 is equal to c. So y is equal to 2x minus x squared plus 8. So we can bring up that curve, and we want to find the area of the finite curve, which we have in green there. So how do we find the area of this in the first quadrant? We can integrate y with respect to x between the limits of 0 and 4. Those limits are taken from the x-axis because we're using dx with respect to x. So if we integrate 2x minus x squared plus 8, because we already worked out what y was, that will be the integral of 2x is x squared minus integral of x squared is x cubed on 3 plus the integral of 8 is 8x between limits of 0 and 4. And if we substitute, it's going to give us 4 squared minus 4 cubed over 3 plus 8 times 4 minus 0 squared minus 0 cubed plus 8 times 0. And that works out to be 144 on 3 minus 64 on 3, which works out to be 80 on 3 units squared. So the area under the curve is 80 on 3 units squared. May 2014, number 5a. The equation of a curve is y is equal to 3 plus 4x minus x squared. And we can bring up a sketch to show such. The point P, 3, 6 lies on the curve. So let's bring up P as well. Find the equation of the tangent to the curve at P, giving your answer in the form ax plus by plus c is equal to 0, where a, b, and c are real numbers. So let's bring up a tangent. As such, the green line appears to be sloping down to the right, so the gradient should be negative. So how do we go about solving this? So since we know the equation of the curve, then we can differentiate it. dy dx will be d dx of whatever y is. So we need to find the gradient of the curve. So let's differentiate that. So dy dx is equal to d dx of 3 plus 4x minus x squared, which is given above. And if we differentiate 3, that will give us 0. And if we differentiate 4x, it will give us plus 4. And differentiate minus x squared, the 2 will come in front, so it will be minus 2x. So the gradient function of any point on this red line graph is 4 minus 2x, which tells us that the gradient changes according to the value of x. So at the point P, when x is equal to 3, we can substitute into there. So dy dx, the gradient at the point P, will be 4 minus 2 times 3. 2 3s are 6, so 4 minus 6, that will give us minus 2. So the gradient is minus 2 or negative at the point P. And we can see that from the slope of the line. So let's recall that the gradient of the tangent is equal to change in y over change in x. So let's substitute. Minus 2 is equal to y minus, and we'll use one point which lies on that tangent, which is P. And we know the y value is 6, so it'll be y minus 6 over x minus 3. And let's make y, the subject of the formula. So let's carry the denominator across. It will give us minus 2 by x minus 3 is equal to y minus 6. And we want one side to be equal to 0. If we look at the form above, ax plus by plus c is equal to 0. So let's carry everything across. So it will be minus 2x minus y plus 6 is equal to 0. So minus 2x minus y plus 12 is equal to 0. And that's the equation of the tangent. May 2014, number 5b. Given that f of x is equal to 2x cubed minus 9x squared minus 24x plus 7, part 1, find all stationary points of f of x. We can differentiate f of x in order to get the stationary points. So dy dx is equal to d dx of 2x cubed minus 9x squared minus 24x plus 7. And if you differentiate it, 2x cubed, 2 times, the 3 will come in front, 2 3s are 6x, and the power will be 3 minus 1, which is 2. So it will give us 6x squared minus 9 2s are 18x minus 24. At the stationary points, the gradient dy dx is equal to 0, so we can substitute 0 is equal to x squared minus 3x minus 4. And we can solve for x here either using the quadratic formula or factorize. I will factorize here, so 0 is equal to x minus 4 by x plus 1. So either x minus 4 is equal to 0, that will be where one stationary point occurs, which means x is equal to 4 at that point. And if we want to find the y value, we need to substitute x as 4 into y. So y is equal to 2x cubed minus 9x squared minus 24x plus 7, which is given. And if we substitute, it will be y is equal to 2 by 4 cubed minus 9 by 4 squared minus 24 by 4 plus 7. And of course, 4 cubed is 64. 2 by 64 is 128 minus 9 times 16, which is 144, minus 96 plus 7. So y is equal to minus 105. So let's bring up that point to indicate one of the stationary points, which is 4 minus 105. And at the other factor, x plus 1 is equal to 0. That means x is equal to minus 1. That's where the second stationary point occurs. So y is equal to 2x cubed minus 9x squared minus 24x plus 7. And we can substitute for x in order to solve for y. So y is equal to 2 by minus 1 cubed minus 9 by minus 1 squared minus 24 by minus 1 plus 7. And using our calculators, or we can work that out mentally, y is equal to 20. So at the point minus 120 will be the other stationary point. Now we're working it out here. Now we're working it out abstractly, but the graph here, which you will not have in the exam, shows the supporting evidence of such, where the stationary points are for the cubic curve. Part 2, determine the nature of each of the stationary points of f of x. So how do we find the nature of it, whether it's a maximum or minimum? First thing we do double differential. So d2y dx squared will be d dx of dy dx. And we already have dy dx, it worked out in our second line in part 1. So if we substitute, it will be d dx of 6x squared minus 18x minus 24. And if we differentiate that, so it will give us 12x minus 18. So when x is equal to 4, which is on the right hand side, it will give us 12 by 4 minus 18, which is something that is positive, greater than 0. So that means it's a minimum point. And when x is equal to minus 1, and we substitute into dy dx squared, it will be 12 by minus 1, which is minus 12 minus 18, which is minus 30, which is less than 0. So that means that's a maximum point. And this solution here supports the graph of the sketch. May 2014, number 6a. Evaluate x by x squared minus 2 with respect to x between the limits of 2 and 4. So what that is really asking us to do is find the area under the graph of x by x squared minus 2 between those limits. We can expand the brackets, so that will give us the integral between 2 and 4 of x by x squared is x cubed minus 2x with respect to x. So if we bring up a graph to show x cubed minus 2x, and we're doing this so students can recognize that finding the integral of this graph between those limits means finding the area under this graph. So we can bring up the line x is equal to 2 from the x-axis up to the curve, and then we bring up the line x equal to 4 from the x-axis to the red line to the curve. So finding the integral of this curve means finding the area under the graph, which we have in green. So we can work it out. The integral of x cubed will give us x to the 4th divided by 4 minus 2x, the integral of which is x squared, between the limits of 2 and 4. So we can now substitute. That will give us 4 to the power 4 divided by 4 minus 4 squared minus 2 to the power 4 divided by 4 minus 2 squared. We're just substituting. And 4 to the power 4 will be 4 fours, will give us 4 times 4 times 4 times 4 divided by a 4. One of these 4s will cancel from above and below. So that will left with 4 cubed, which is 64, minus 4 squared is 16, minus 2 times 2 times 2 times 2. 2 2s are 4 on top, will cancel with the 4 in the denominator. So we're left with 4 minus 2 squared, which is plus 4. So we have 64 minus 16 is 48. 48 minus 4 is 44, plus 4 is 48. So that tells us that the area that we have represented there in the graph is 48 square units. Part B. Evaluate 4 cos x plus 2 sin x with respect to x between the limits of 0 and pi on 3, leaving your answer in solid form. So if we bring up a sketch of that graph, 4 cos x plus 2 sin x, which we have in red, this is not necessary for the solution, but it is necessary for students to get a grasp of what is happening. So finding the integral would mean finding the area under this curve. Between the limits x is equal to 0, so we can bring that up as a green line along the y-axis, and x is equal to pi on 3, which we have in a black line there. So therefore, what we're asking us to find is the area, which we'll indicate in light blue, under the curve between those limits. So we can work it out precisely using integration. So if we integrate 4 cos x, it's going to give us 4 sin x minus 2 cos x between the limits of 0 and pi on 3. So now that we've integrated this definite integral, and because it's a definite integral, we don't need to write the plus c, the constant of integration, because if you write it, it will cancel out anyhow. Now that we have integrated, we can substitute. So 4 sin pi on 3 minus 2 cos pi on 3 minus 4 sin 0 minus 2 cos 0. And sin pi on 3, remember pi on 3 is 180 divided by 3, which is 60 degrees. So sin 60 is root 3 on 2. So we can substitute. It's going to give us 4 times root 3 on 2 minus 2 cos 60. And cos 60 is a half. So minus 2 times a half minus 4 sin 0. And sin of 0 is 0. Plus 2 cos 0. And cos 0 is 1. So we can work that out. 2 into 2, 1, 2 into 4, 2. So we get 2 root 3 minus 2 times a half is minus 1 minus 0 plus 2. Minus 1 plus 2 is 1. So the area under the curve is 2 root 3 plus 1 square units. May 2014, number 6C. A curve passes through the point P, 2 minus 5, and is such that dy dx is equal to 6x squared minus 1. Part 1. Determine the equation of the curve. So we know the gradient of the curve, dy dx is equal to 6x squared minus 1. So if we integrate both sides with respect to x, it should be able to give us y. So if we integrate, the left-hand side becomes y is equal to 6x squared. When integrated, will be 6x cubed on 3, and 3 into 6 is 2. So that will give us 2x cubed minus x plus c, the constant of integration. And if we want to solve for c, we know that this curve y is equal to 2x cubed minus x plus c is passing through the point P, where the values of x and y are known. So we can substitute them. So that will give us minus 5 is equal to 2 by 2 cubed minus 2 plus c. So minus 5 is equal to 2 by 2 cubed is 16, minus 2 is 14. Move that to the left-hand side. Minus 5 minus 14 is minus 19 is equal to c, the constant of integration. So the equation of the curve is y is equal to 2x cubed minus x minus 19. Part 2. Find the area of the finite region bounded by the curve, which we worked out in part 1. The x-axis, the line x is equal to 3, and the line x is equal to 4. So since they're asking us to find the area, we can write that as area is equal to integral of y dx between the limits of 3 and 4. And we can substitute for y, because we know that from part 1. So area is equal to the integral between 3 and 4 of 2x cubed minus x minus 19 with respect to x. And we can integrate, so that will give us 2x to the 4th divided by 4, which is equal to x to the power 4 divided by 2 minus x squared divided by 2 minus 19x plus c between the limits of 3 and 4. The constant of integration will cancel out, and we can leave out the plus c if you wish. Now we can substitute for 4 and 3, so that will give us 4 to the power 4 divided by 2 minus 4 squared divided by 2 minus 19 times 4 minus 3 to the power 4 divided by 2 minus 3 squared divided by 2 minus 19 by 3. So 4 to the power 4 divided by 2 is 128, minus 4 4s are 16, 2 into 16, 8, minus 19 by 4 is 76, minus 3 to the power 4, which is 81 divided by 2, plus 3 squared is 9 over 2, plus 57. And that works out to be 65 square units. So that will be the area under the curve of that finite region. May 2015, number 5a. Differentiate the following expression with respect to x, simplifying your answer. 2x squared plus 3 in brackets times sine 5x. So if you want to differentiate that, let's write it as d dx of 2x squared plus 3, we have that in purple, times sine 5x. And why we're doing that is so that students can recognize that it is the product rule that we're using. We're differentiating u, v, so we have them in different colors, and that will give us u dv dx plus v du dx. So we can simply substitute. We know u is 2x cubed plus 3. We know v is sine 5x and the differentials of those. So this will give us 2x squared plus 3 d dx of sine 5x plus sine 5x d dx of 2x squared plus 3. So it's a simple substitution. And if we differentiate, that will give us 2x squared plus 3 by, what's the differential of sine 5x? 5 cos 5x. Plus sine 5x by the differential of 2x squared plus 3 is 4x. So that will give us 10x squared plus 15 cos 5x plus 4x sine 5x. B, part 1. Find the coordinates of all the stationary points of the curve y is equal to x cubed minus 5x squared plus 3x plus 1. So let's recall that when we want to find the stationary points of a curve, we know at those points that the gradient is 0. So we want to find dy dx. So dy dx is d dx of x cubed minus 5x squared plus 3x plus 1. So dy dx is equal to, when you differentiate x cubed, it will give us 3x squared. We differentiate minus 5x squared. 5 2s are 10, so it will give us minus 10x plus 3x. When differentiate that, will give us plus 3. And we know for the stationary points, dy dx is equal to 0. So we can substitute 0 is equal to, and we could factorize that quadratic equation on the right hand side. It will give us 3x minus 1 by x minus 3. As such, 3x minus 1 is equal to 0, which implies that x is equal to 1/3. So that is one coordinate of one of the stationary points. And how do we find the y value of that? We can substitute x equal to 1/3 into the equation of the line. So let's rewrite the equation. Y is equal to x cubed minus 5x squared plus 3x plus 1. And substitute where x is 1/3. So it'll give us y is equal to 1/3 cubed minus 5 by 1/3 squared plus 3 by 1/3 plus 1. So y is equal to 40 over 27. As such, one of the stationary points will have coordinates 1/3 by 40 over 27. And if the first bracket isn't 0, then the second bracket will be 0. So or x minus 3 is equal to 0, which implies x is equal to 3. So that's the x coordinate of the second stationary point. And if we substitute just as we did before, so let's now rewrite the equation y is equal to x cubed minus 5x squared plus 3x plus 1, and substitute for x is equal to 3 into that. So y is equal to 3 cubed minus 5 by 3 squared plus 3 by 3 plus 1. So y is equal to minus 8. So the second stationary point will have coordinates 3 minus 8. Part 2. Determine the nature of each point in part 1 above. So how do we find the nature of the points? We can do a double differential. So d2y dx squared, what is that? That's equal to the differential of dy dx. And we have dy dx from the second line above. That is equal to d dx of, what is dy dx? 3x squared minus 10x plus 3. So if we differentiate that, that's going to give us 3 2s are 6x minus 10. And when x is 1/3, which is the first stationary point, and we substitute it into d2y dx squared, it will give us 6 by 1/3 minus 10. 6 by 1/3, 3 into 3, 1, 3 into 6, 2. 2 minus 10 is negative. is less than 0. And when d2y dx squared is less than 0, it means that it is a maximum point. And similarly, let's do that for when x is equal to 3, the other stationary point. And when we substitute, it'll give us 6 by 3 minus 10. 6 to the 18 minus 10 is 8. And since d2y dx squared is greater than 0, it means we have a minimum point. So if we bring up a sketch of the curve, we can see where the maximum and minimum points lie. May 2015, number 5C. A spherical balloon of volume V is equal to 4/3 pi r cubed is being filled with air at the rate of 200 centimeter cubed per second. Calculate, in terms of pi, the rate at which the radius is increasing when the radius of the balloon is 10 centimeters. So we know the volume is 4/3 pi r cubed, and if we differentiate that, so dVdr will give us 4/3 pi, that's a constant, times 3r squared. And the 3 will cancel, so we're left with 4 pi r squared. Since this is a rates of change question, we know dv dt would be equal to dv dr times dr dt. And if students are getting problems with this, we can just recognize on the right hand side, all we're doing is imagining their fractions and they're cancelling out. So the dr will cancel out on the denominator and numerator and be left with dv dt. So do we have dv dr? Yes, we do. We just worked that out. So that is 4 pi, and we know r is 10. So 4 by pi by 10 squared. So now that we have that equation, we can substitute. We know dv dt, the volume per second, which is 200, is equal to dv dr, which we just worked out above, 4 times pi times, and how much is r? 10 squared times dr dt. And 4 times pi times 100 is 400 pi. So if we carry that across, it will give us 200 over 400 pi. So that will give us 1 over 2 pi centimeters per second is equal to dr dt. As such, the rate at which the radius is increasing when the radius of the balloon is 10 centimeters is 1 over 2 pi centimeters per second. May 2015, number 6A. Evaluate cos 3 theta with respect to theta between the limits of pi on 6 and pi on 3. So what they're really asking us to find is the area under that graph of cos 3 theta. So let's bring up that sketch and let's identify pi on 3, that point there on the x-axis, and let's draw a vertical line down to meet the curve. So that will be that limit, and pi on 6, which is where the curve is cutting the x-axis. Let's bring up that blue compound area. So when we're evaluating cos 3 theta with respect to theta, what we're doing is finding the area between that curve, which we have in red, and the x-axis, between those limits. And we can see here that the area is under, means that the area should be negative. So let's go solve it. Let's recall that the integral of cos ax dx is equal to 1 on a sine ax plus c. So the integral of cos 3 theta d theta within those limits would be 1/3 sine 3 theta between the limits of pi on 6 to pi on 3. So if we substitute, it's going to give us 1/3 by sine 3 times pi on 3 minus sine 3 times pi on 6, which works out to be 1/3 of sine pi minus sine pi on 2. And we know sine pi, or sine 180 degrees, is 0. So we could substitute equal to 1/3 by 0 minus, and what is sine of 90? 1. So that will give us minus 1/3 square units will be the area under that curve, which is the same as saying what is the integral of cos 3 theta between those limits. Part B. A curve has an equation which satisfies dy dx is equal to kx by x minus 1, where k is a constant. Given that the value of the gradient of the curve at the point 2, 3 is 14, determine part 1, the value of k. So if dy dx is equal to kx by x minus 1, and we know the gradient of the curve, and we also know the x value, therefore the only thing that's unknown would be k. If we substitute dy dx as 14 and x is equal to 2, then that gives us 14 is equal to k by x, or 2 squared, minus kx, which is k times 2. So if we look at this line, we have one unknown, so we should be able to solve for k. 14 is equal to 2 squared, which is 4k minus 2k. 4k minus 2k is 2k. So 14 is equal to 2k, as such 7 is equal to k. So we solve for 7. Part 2. Determine the equation of the curve. So since we know dy dx is equal to 7x by x minus 1, because we worked out for k in part 1, we can expand. So dy dx is equal to 7x squared minus 7x. And we want to find the equation of the curve, so we want to find y. So how do we do that? We integrate both sides with respect to x. So when you integrate dy dx with respect to x, that will give us y is equal to 7x cubed on 3 minus 7x squared on 2 plus c, the constant of integration. This is an indefinite integral, and we can substitute for x and y because we know that curve is passing through the point 2, 3. So 3 is equal to 7 on 3 by 2 cubed minus 7 on 2 by 2 squared plus c. So 3 is equal to 2 cubed is 8. 8 sevens are 56 over 3 minus 2 squared is 4. 2 into 4, 2. 2 sevens are 14 plus c. As such, c is equal to minus 5/3. And since we solved for the constant of integration c, the equation of curve is given by y is equal to 7 on 3 x cubed minus 7 on 2 x squared minus 5 on 3. May 2015, number 6c. Calculate, in terms of pi, the volume of the solid form when the area enclosed by the curve y is equal to x squared plus 1 and the x-axis from x equal to 0 to x equal to 1 is rotated through 360 degrees about the x-axis. So what they're asking us to find is the volume of revolution of this. And the formula is volume is equal to pi by the integral of y squared dx between the limits of a and b for the volume of revolution. If we bring up a curve, so let's substitute for y, so that will give us v is equal to pi times the integral of x squared plus 1 squared with respect to x between 0 and 1. Because if we look at what's given above, it's from x equal to 0 to x equal to 1. Easiest way to do this might be to expand the brackets. So v is equal to the pi times the integral between 0 and 1 of x to the 4th plus 2x squared plus 1 dx. And so as we bring up that curve, let's also bring up the limits where x is equal to 0 as a blue line and x equal to 1 as a black line, both coming from the x-axis. And we can bring up the area under the graph as a green area. And what we want to find is the volume. So let's show a little rotation about the x-axis so you can follow what's happening. And how do we find that volume? We need to integrate accordingly. So let's continue. If we integrate, the volume will be equal to pi times x to the 5th on 5 plus 2x cubed on 3 plus x between the limits of 0 and 1. And we can substitute for 1 and 0. So that will be pi by 1 to the 5th, 1 to the power 5 over 5 plus 2 times 1 to the power 3 over 3 plus 1 minus 0 to the power 5 over 5 plus 2 times 0 to the power 3 over 3 plus 0. And we know the whole right hand side works out to be 0 easily. So v is equal to pi by 1/5 plus 2/3 plus 1. So that works out to be the volume is equal to 28 pi over 15 cubic units. May 2016, number 5a. Find dy dx given that y is equal to the square root of 5x squared minus 4. Simplifying your answer. So let u is equal to 5x squared minus 4. What is inside the square root? As such, y is equal to the square root of u. Or we can write it u to the power a half. So since we know u, we can find du dx, which works out to be 10x. And if y is equal to u to the half, then dy du is equal to half u to the minus a half. So dy dx is equal to dy du times du dx, which is a half u to the minus a half times 10x. So a half of 10 is 5, so that will give us 5x all over the square root of whatever u is, which is 5x squared minus 4. Part B. The point P, 1, 8, lies on the curve with the equation y is equal to 2x by x plus 1 squared. So let's bring up a sketch of the curve in a green line and indicate where P is, which is at 1, 8. Determine the equation of the normal to the curve at the point P. So we can get the tangent of the curve, which is a red line at that point, and the normal would be perpendicular to that. So this is just to give the students a visual representation of what is happening. If we know y, we can find the gradient dy dx, and dy dx will be the d dx of whatever y is. So dy dx is d dx of 2x by x plus 1 squared. We can expand it, so dy dx is d dx of 2x by x squared plus 2x plus 1. And we can multiply throughout by 2x, so dy dx is equal to d dx of 2x cubed plus 4x squared plus 2x. And there are other ways to do this as well. So if we want to find dy dx, let's differentiate that. That will give us 6x squared plus 8x plus 2. So we know the gradient function throughout this cubic equation, and we're looking specifically at the point P where x is 1. So if we substitute when x is equal to 1 into dy dx, that will give us 6 by 1 squared plus 8 by 1 plus 2. So dy dx, which is the gradient of the tangent, which we have in red, will be equal to 6 plus 8 is 14 plus 2 is 16. And we can see that because this line is sloping up to the right. And since the tangent and the normal are perpendicular to each other, then the gradient of the tangent, mt, times the gradient of the normal is equal to minus 1. And we know the gradient of the tangent, we just worked that out, which is 16. So we'll get 16 times the gradient of the normal is equal to minus 1. So the gradient of the normal is equal to minus 1 over 16. And the gradient of the normal will be equal to change in y over change in x. And if we substitute, we're going to get minus 1 over 16 is equal to y minus, and the normal passes through the point P, so we know the x value is 1 at that point and the y value is 8. So we can substitute, and that will give us minus 1 over 16 is equal to y minus 8 over x minus 1. The 1 and the 8 coming from the coordinates of P. And we can make y the subject of the formula by carrying the denominator across. So it will be minus 1 on 16 times x minus 1 is equal to y minus 8. So we could expand the brackets and carry across the minus 8. So it will be minus 1 on 16 x plus 1 on 16 plus 8 is equal to y. As such, the equation of the normal is y is equal to minus 1 on 16 x plus 8 and 1/16. May 2016, number 5c. Obtain the equation for each of the two tangents drawn to the curve y is equal to x squared at the points where y is equal to 16. So let's bring up the curve y is equal to x squared. And we can substitute for y, which is 16, is equal to x squared. So x is equal to the square root of 16, which is plus or minus 4. Which means when x is plus 4, y is 16. That's one coordinate. Let's call that A. So we can bring up that point. And when x is minus 4, x is still 16. So let's call that point B. So we have 2 points. And we want to get the tangents at both points. So in order to get the gradient, dy dx will be d dx of what is y? X squared. So dy dx is equal to 2x. So when x is equal to 4, which is at A, then the gradient dy dx is equal to 2 times 4. So dy dx, which is the gradient of the tangent at A, is equal to 8. And the gradient of the tangent is equal to change in y over change in x. And we're using the values at A, which is 4 and 16. And we know the gradient is 8, so we can substitute. So that will give us 8 is equal to y minus 16 over x minus 4. And let's make y the subject of the formula. So let's carry the denominator across. So that will give us 8 by x minus 4 is equal to y minus 16. And let's expand the brackets and carry the 16 across. So it will give us 8x minus 32 plus 16 is equal to y. As such, the equation of the tangent at A is y is equal to 8x minus 16. And let's do the same thing for the point B when x is equal to minus 4. So dy dx is equal to 2 times minus 4. So dy dx, which is the gradient of the tangent at B, is equal to minus 8. So the gradient of the tangent b is equal to change in y over change in x. And we know the gradient of the tangent, that's minus 8. And we know the coordinates of the point b, which is minus 4, 16. So we can substitute. So minus 8 is equal to y minus 16 over x minus 4. Let's make y the subject of the formula. So let's carry the denominator across. It will give us minus 8 by x plus 4 is equal to y minus 16. Let's expand and carry the minus 16 across. It will give us minus 8 minus 32 plus 16 is equal to y. As such, the equation of the tangent at B would be y is equal to minus 8x minus 16. May 2016, number 6a. Find the integral of 3 cos theta minus 5 sin theta d theta. So this is an indefinite integral, which means that our answer will include c, the constant of integration. So when we integrate, it will give us 3 sin theta plus 5 cos theta plus c. Part 2. Evaluate the integral of 2 over x squared minus 3 plus 2x cubed dx between the limits of 1 and 3. So if we integrate, it will give us minus 2 over x minus 3x plus 2 over 4x to the power 4 between the limits of 1 and 3. And if we substitute, it will give us minus 2/3 minus 3 by 3 plus 2 on 4 times 3 to the power 4 minus 2 on 1 minus 3 by 1 plus 2 on 4 by 1 to the power 4. So that will give us minus 2/3 minus 3 by 3 is minus 9 plus 81 over 2 minus 2 is plus 2 minus 3 by 1 is plus 3 minus a half. And that works out to be 212 over 6 units squared. Part B, the following figure shows the finite region R bounded by the lines x equal to 1, x equal to 2, and the arc of the curve y is equal to x minus 2 squared plus 5, and of course the x-axis. Calculate the region R, which is the area. So let's recall the area under a curve is equal to integral of y dx between the limits a and b. And we can substitute. So area is equal to the integral of x minus 2 squared plus 5, which was given as y above, between the limits of 1 and 2 with respect to x. So we can expand. It will give us x squared minus 4x plus 4 plus 5 will give us plus 9. And if we integrate such, it will give us x cubed on 3 minus 2x squared plus 9x between the limits of 1 and 2. So we can substitute just as we did in A part 2. So it will give us 2 cubed over 3 minus 2 by 2 squared plus 9 by 2 minus 1 cubed over 3 minus 2 by 1 squared plus 9 by 1. And that works out to be 8 over 3 minus 2 2s are 4 by 2 minus 8 plus 18 minus 1/3 plus 2 minus 9. And that works out to be 16 over 3 square units. And we can see the area is above the x-axis. As such, the area must be positive. May 2016, number 6c. The point P, 1, 2, lies on a curve which has a gradient function given by dy dx is equal to 3x squared minus 6x. Find the equation of the curve. So if we know dy dx is equal to 3x squared minus 6x, we can integrate both sides with respect to x. So the left-hand side will give us y is equal to x cubed minus 3x squared plus c. And we've almost solved the equation. We just need to find for c the constant of integration. And since we know the point is passing through P, which is 1, 2, then we can substitute for y and x into the equation. So it will give us 2 is equal to 1 cubed minus 3 by 1 squared plus c. So 2 is equal to 1 cubed, which is 1, minus 3 by 1 squared, which is minus 3, plus c. So c works out to be 4. As such, the equation is y is equal to x cubed minus 3x squared plus 4. We have now come to the end of CSEC past paper questions in the major section of Introductory Calculus. In this video, we looked at past paper questions from 2012 until 2016. And in our next video in this series, we'll be looking at past paper questions from 2017 until 2022. So don't forget to look at the description down below where we have suggested an order that you go through the entire CSEC syllabus past paper questions so you can get a better grasp of the subject area.